Hi dear students, in this presentation we will be discussing about heat treatment. We know that based on the composition of the carbon present, the steel will have different structure, and also based on the cooling rate also the properties of the steel will be different. So by altering nature, size, shape and distribution of various micro components, various mechanical properties of steel are obtained. This altering is done by heat treatment. So heat treatment, it is not heat transfer. So heat treatment is defined as an operation or continuation of operations involving heating and cooling of a metal or alloy in a solid state to obtain desirable properties. So actually heat treatment is heating and cooling or continuous operations of heating and cooling of a particular metal to obtain the desirable properties. Sometimes we wish to have particular properties, so which property we want, ultimately based on that we will be fixing the cooling rate as well as the heating rate. So based on that the final structure of the steel also will be different. The micro structure formed, or the if you look through the microscope, the structure of the steel will be different based on this cooling rate and even based on the composition also. So iron, you might have studied about iron carbon equilibrium diagram in the previous presentation. So in that mainly we are discussing about the different phases coexisting based on the carbon percentage, but here we will be mainly discussing about the how the cooling rate or time elapsed for cooling is affecting the properties of the steel. So that is not discussed in the iron carbon equilibrium or phase diagram. Here we will be mainly discussing about the how the difference in the cooling rate will affect the properties of the steel. That is what is known as heat treatment. Sometimes we will be cooling the material at a quicker rate. In that case the properties obtained and the chemical structure obtained both will be different, whereas if you cool the particular metal after heating in a very slow rate, then the property obtained will be entirely different than the other one. So a lot of difference is there. So we will be studying in detail about how these cooling rates are having an effect on the properties of the steel. So it is normally carried out first by heating it in solid state and then cooling it. So heat treatment is a simple process. What we will do is, during the heat treatment process we will heat a particular steel component in its solid state itself. We won't let it to go into the liquid state. So within the solid state itself we will heat it, and after heating or reaching the required temperature and maintaining at a particular temperature for the required time, then it is allowed to cool in a particular environment. So that cooling rate will decide which property finally we will have, which structure finally we will have. Okay, so anyway, by studying this one we will have a clear idea at the end of this presentation. So stages usually involved in these processes are: stage 1, heating the metal to a specified temperature. So initially we will heat the metal to a or steel to a specified temperature. Usually we will be heating to a upper critical temperature, and usually the most stable component in that state will be the austenite, which you have studied during phase diagram. Stage 2, holding the metal at increased temperature for a specified time. So once the temperature is reached to the required level, we will be holding the metal in that temperature for a specified time. Then that's in step 3. Finally we will be going for the cooling process. It is simply known as quenching. Okay, now objectives of the heat treatment are these 8 points are the objectives of treatment. By doing heat treatment we will have all these advantages, or these are the main objectives of heat treatment. First one is to relieve internal stresses which are set up in the metal due to cold working or hot working. So due to the cold working or hot working, anyway we will be discussing about cold working and hot working in detail in the fourth module. So anyway I will give you a small idea about cold working and hot working. If the heating temperature is less than the recrystallization temperature of a particular material, then we will call that process cold working. If the heating is more than the recrystallization temperature, or by heating if the recrystallization taking place within the metal, then we will call it as hot working. So during cold working there is no recrystallization. So if you are hammering or doing some mechanical processes on the particular material in the cold working temperature range, then there can be possibility of lot of stresses developed within the material. So localized stresses can be there within the material. By doing the heat treatment, the first aim is to relieve the internal stresses caused by this cold working or hot working. The next objective is to soften the metal. And third one is to improve hardness of the metal surface. Sometimes to use it as a cutting tool and all, we have to impart the hardness to the at least to the surface. That is what is done by some of the heat treatment process. Now next one is to improve machinability. See, if you are making the metal soften, then we will be improving the machinability. Both are different things. See, sometimes we will be providing the hardness to the surface, sometimes we will be making the metal softer. So all these are done by different processes. By doing a particular heat treatment, sometimes we will be getting the metal as softer one. By doing another heat treatment process, we will be getting a harder surface also. So anything is possible by doing heat treatment, but only we have to choose that appropriate method of heat treatment which based on which property we require at the end of the process. Next is to refine grain structure, and the sixth one is to improve mechanical properties like tensile strength, ductility and shock resistance, etc. Next one is to improve electrical and magnetic properties, and finally to increase the resistance to wear and tear and corrosion, etc. So in order to obtain all this, we are going for the heat treatment processes. Now before moving on to the hardcore of the heat treatment processes, we must have a basic idea about isothermal transformation diagrams, or simply it is called time temperature transformation diagram. In short, it is called TTT diagram. That is a simple word. Okay. So before moving to the heat treatment, we must have a clear idea about these things, TTT, as well as one more curve is there, CCT, that also is required. So in this presentation, instead of going mainly into the heat treatment process, we will be discussing about this thing, that is TTT diagram. The iron carbon phase diagram does not show time as variable, hence cannot show the effects of various cooling rates. See, in the last topic you have studied iron carbon equilibrium diagram. In that, time is not taken in any of the axes. So what effect will be there on the cooling rate if you are cooling in a quicker time, or fast cooling if you are cooling in a slow environment, or slow cooling is provided. So both will have the different effect, I have already told. So that data is not available from the phase diagram. That's why we go for time temperature transformation diagram. TTT diagram can be used for this purpose. It is also known as S curve or C curve due to their shape. Sometimes question will be like this, discuss about S curve or C curve. All are same. Time temperature transformation diagram is simply known as, sometimes it is known as S curve or C curve because of its shape. Okay, see, its shape will be something like this, S shape. So that's why it is known as S curve. Okay. It shows what structure can be expected after various rates of cooling. So in a simple sense, TTT diagram shows what structure can be expected after various rates of cooling. So what will happen if you cool in a slower rate? What will happen if you cool in a faster rate? So what structure we will expect to get finally, that idea we will get from this TTT diagram. It graphically describes the cooling rate required for the transformation of austenite to perlite, bainite or martensite. You know that while cooling, what happens is the most stable structure, that is austenite, is transformed into perlite. Perlite means it's a combination of ferrite plus cementite. So either we will be getting perlite, sometimes we will be getting bainite, or sometimes even we will be getting martensite. These are the different forms available based on the cooling rate. If you provide enough time for cooling or slow cooling, then usually we will be getting perlite. Otherwise, in medium cooling, we will be obtaining bainite, and if it is much quicker cooling, then instead of converting austenite into perlite and cementite, we will be directly getting another structure, that is what is known as martensite. That is, austenite is not completely transformed into cementite and not completely transformed into ferrite and cementite. Okay. The TTT diagram indicates the extent of transformation as a function of time for a continuously decreasing temperature. Samples are austenitized and then cooled at a predetermined rate and the degree of transformation is measured, for example, by dilatometry. The process is called dilatometry. So we will cool that particular specimen to be tested. Sorry, we will heat the particular specimen to be tested into a required temperature. So in that required temperature, of course, the temperature will be higher than the upper critical temperature that you have studied in the phase diagram. So usually in that structure, in that condition, the specimen will have most stable form, that is austenite. So on cooling, then what we will do is we will be cooling on the predetermined rate and the degree of transformation is measured. So finally what structure we are obtaining, that we will measure using the method known as dilatometry. Okay, so now we will discuss how to obtain TTT diagram. Consider a small specimen of steel heated continuously from room temperature to temperature above the critical temperature. So we are heating that specimen to a temperature above critical temperature. At this temperature, steel is in the form of stable austenite. I have already told, above the critical temperature, steel will have the stable structure, that is what is known as austenite. Now let this specimen be cooled isothermally in a bath. Bath isothermal means constant temperature. So we are allowing this specimen, that heated specimen, to cool by putting it into a isothermal bath. Isothermal bath means constant temperature bath below critical temperature. So usually the bath temperature will be less than the critical lower critical temperature, that is 727 or 725. In some text it is given as 725 degrees Celsius for steel. In some text it is 727, whatever it may be. So always the bath temperature at which we are cooling it is kept as below lower critical temperature, that is less than 727 degrees Celsius. Say initially we are keeping the isothermal bath at 650 degrees Celsius. So the liquid contained in the bath will have the 650 degrees Celsius temperature always. So it is isothermal. It is kept, the bath is in the isothermal temperature, or the temperature of the bath is kept as constant. So say at 650 degrees Celsius. See here you can see from the figure. See the furnace is there for the heating of the specimen, and the specimen is heated to a temperature higher than that of the critical temperature, and the structure obtained is austenite. Austenitic temperature, we will call it as austenitic temperature. So we will be heating it for a particular time period. After once all the part of the specimen has got heated enough for uniform temperature, once uniform temperature is reached, then what we will do is we will be rapidly transferring that specimen into the molten salt bath. In this molten salt bath we will be setting the constant temperature, that is 650 degrees Celsius. So samples are kept here for varying time rapid transfer. So based on the temperature of this molten bath, the cooling rate also will be decided. If the molten bath temperature is very high, see around 700 degrees Celsius, that means the cooling will be very slow cooling. If the molten bath salt bath temperature is very low, that means fast cooling will take place, because if the temperature difference is more, then the heat transfer will be more. Now once it is finished, then we will be going for the final process, that is water quench at room temperature. So after that it is transferred into the water bath for the final processing. So that is what is experimental side. So I have already told we will be examining all the physical transformations happening through the microscope and all, and structures we will analyze. At this temperature, austenite is unstable and hence it transforms into a mixture of ferrite and cementite. As we see that, see at the initial stage, if the temperature is above critical temperature, then what happens is the specimen will have the stable structure, that is what is known as austenite. So once cooling starts and the temperature is below lower critical temperature, that means below 727 degrees Celsius, what that means, the austenite cannot be no longer in the stable state. So it will change its structure from it will transform its structure from austenite state to ferrite and cementite state. Okay, now if we plot the result on a graph with amount of austenite transformed on vertical axis, see here we have a graph plotted based on this experimental data. Here we will be taking the percentage of amount of austenite transformed in the vertical axis and the time elapsed, usually not in seconds and hour, usually it is in the logarithmic time scale along the horizontal axis. So time for that process to complete, or the transformation from austenite to ferrite plus cementite structure is noted down in each and every time. So that we will plot it as a graph, then you will get a graph shape like this. This is something like a S shape, that's why it is also known as S curve. Okay, so the curve obtained is called the isothermal curve. So now the curve obtained is simply known as isothermal curve. Why it is isothermal curve is the temperature of the bath is kept as constant. So in a constant temperature, austenite is gradually transformed into ferrite plus cementite. So gradually that transformation is taking place. You can see from this figure at the point A, you can see a point A marked at the bottom, at the horizontal axis, in between 1 and 10 you can see a point marked as A. At that point A, we can see that the structure, the specimen is completely having austenite structure, no ferrite and cementite is present there. So from that particular time point to, as the time goes on, the cooling gradually processes. So what happens is, slightly the austenite is no longer stable, I have already told. So that unstable austenite will start to transform into ferrite and cementite. So gradually ferrite and cementite structure will be formed within the solid which is getting cooled in the bath. So that transformation will take some time. So at point, once the time reaches corresponding to that point B, so by this much time, uh, complete transformation of the austenite into ferrite and cementite will take place. So the process start at point A, and within the process will end at point B. So at point A we will have complete austenite structure, and at point B we will be having complete ferrite plus cementite structure. There is no austenite present at the point B. So this is what is happening within that time period, and it is plotted, and the curve is known as isothermal curve. I hope this isothermal curve is clear for you, and this curve is for a particular temperature of 650 degrees Celsius. That means the constant bath temperature is kept as 650 degrees Celsius. We can do this experiment for different temperatures like 500 degrees Celsius, 400 degrees Celsius, 250 degrees Celsius, etc. So similarly, we will get similar structured curves for the different temperatures. The shape will be almost same. That is, that S shape we will maintain, but only difference is the cooling rate will be different, and of course the time required for the complete transformation also will be different. So if you the steel at point A has a austenite structure, and at point B its structure is a mixture of ferrite and cementite. That combination, ferrite plus cementite, is simply known as perlite. So that's combination of ferrite plus cementite is simply known as perlite. Now, if we cool the steel from upper critical temperature to different temperatures, say 500 degrees Celsius, 400 degrees Celsius, 250 degrees Celsius, etc., and plot the graph as shown below, we'll get a graph something like this. This upper portion, see, this curve is for the 500 degrees Celsius. This S curve stands for the 500 degrees Celsius transformation at point A. A is the starting point for the that particular transformation process at 500 degrees Celsius, and B is the finishing point. Similarly, here you can see, and for 400 degrees Celsius this is the curve, and for 650 degrees Celsius this was the curve obtained, and for 250 this was the curve obtained. Okay, so all these curve we can plot in a particular diagram. That is what that diagram is known as isothermal curve. Now draw another graph with the temperature along vertical axis and time along horizontal axis. Now we are drawing another graph. To analyze all these things, we are drawing another graph with the temperature along vertical axis and time along the horizontal axis. Of course, logarithmic time we will be drawing. So initially in the earlier curve, along the vertical axis we have taken the percentage of, or the amount of austenite transformed. Here you can see this one is the amount of austenite transformed, but in the next curve, instead of that one, we will be taking the temperature. You can see in the vertical axis we will have the temperature, and horizontal axis is same as that of the earlier one. Time in the exponential form we will be considering. Now the time elapsed from beginning to the end of the transformation is marked in the isotherm by projecting them from isothermal curve. See, the advantage of this curve is, you can see, we have conducted experiment for 500 degrees Celsius, 400 degrees Celsius, 650 degrees Celsius, and 250 degrees Celsius. All these can be represented here as a horizontal line, since this vertical axis temperature. So This horizontal line, this dotted horizontal line shows the temperature for 250 degrees Celsius. This dotted horizontal, the next one is for 400, next dotted line is for 500, and next one is for 650. So all 650 constant temperature line, 500, 400 and 250, all the temperature or the isotherms we have drawn in this graph. Now to that same line we will be drawing the we will be marking the starting and uh, finishing point of the transformation, that is say for this one is for 500 degrees Celsius. See, the starting point is this one, this is A2 I think. So we will be dropping that A2 line to the 500 temperature line. So here you will get the intersection, this is point A2. The final point or the final point of transformation for this 500 degrees Celsius is B2. So from B2 I will be dropping a line to meet the same 500 degrees Celsius. That means A2 is the starting point of transformation for the process in the 500 degrees Celsius, and B2 is the final transformation point for the 500 degrees. Similarly, we can get the starting and final process for different temperatures. Say for 650 degrees Celsius, A1 is the starting point. I have drawn a perpendicular to the horizontal line drawn through 650 degrees Celsius. So the meeting point is A1. Similarly, B2 is the final point of the transformation. From there I have dropped a line to the same 650 degrees Celsius line. Here you will get the B2 point. Similarly, I got A2, A1, B1 I got, A2, B2 I got, A3, B3. A3, B3 stands for 400 degrees Celsius, and A4, B4 stands for the 250 degrees Celsius. So I got A1, A2, A3, A4. All these points will be the starting point of the transformation, whereas B1, B2, B3 and B4 are the finishing point of the transformation. So I have drawn a curve joining A1, A2, A3 and A4. You will get a curve like this, and joining B1, B2, B3 and B4 you will get a curve like this. See, the shape of the curve is actually a C shape. That's why it is also known as C curve. Okay. So this diagram finally obtained is called isothermal transformation diagram. Okay. So what you can conclude from this figure is, see, to the left of this curve, that is innermost, you can see a curve joining A1, A2, A3 and A4. To the left of this curve, the structure of the steel is a stable state, that is what is known as austenite. So and in this entire region, the structure of the steel is stable and it is known as austenite. So after B, complete transformation has happened. So in between, the transformation will be taking place. So in between the region of these two curves, this region, this entire region, the structure will be completely ferrite plus cementite, or we'll call it as simply pearlite. Okay. So after transformation, what will be there, that we have to discuss, that we will discuss in the next with the next graph. Anyway, this shape obtained in the C shape is simply known as TTT diagram. Okay. So this is the method how we will obtain the TTT diagram. Now the left hand curve shows the beginning of the transformation of steel, and right hand side indicates end of the transformation. The transformation proceeds in the area located between these two curves, and hence austenite and pearlite coexist in that region. So within this region, we can say that the complete transformation has not taken place. So some portion will be as austenite itself, some has already transformed to ferrite plus cementite, that is pearlite. So both pearlite and austenite coexist within that region. A slow cooling rate at the temperature just below the eutectoid, as indicated by the curve 1, yields coarse pearlite. So that we can see from here. So now we will be discussing what will be the effect of different cooling rates on the final structure produced. So for that I am providing some cooling rates. See, this is 1 indicates the slow cooling rate. That means in a very slow rate cooling is happening. That means the cooling is, see, I have already told the temperature of the specimen in the austenite region is just above 727 degrees Celsius. From that temperature to I am bringing the temperature to around 750, around 650 temperature range only. So that means temperature difference is hardly 50 to 100 degrees Celsius. So that means if the temperature difference is less and the time required for the temperature to achieve is very high, that means the cooling rate we can call it as very slow cooling. If the temperature difference is much higher and the time required is less, that means we will call it as faster cooling. So the curve 1, you can see a dot line here, this one is slowest cooling curve, and 2 is an intermediate cooling curve, and 3 of course is the highest cooling fastest cooling rate. That means from this 727 or 725 degrees Celsius to almost for 400 degrees Celsius difference, that much difference is there. That means almost above 300 degrees Celsius difference is there, and you can see the time between that cooling is only very small. That means the third curve is the fastest cooling rate. So now I will discuss what happens if the cooling rate is less, and medium, what will happen if we cool in a medium rate, and if we cool in a fastest rate. So that we will discuss one by one. First one is a slow cooling rate at the temperature just below the eutectoid as indicated by the curve 1 yields cos light. If the cooling rate is very less or slow cooling rate is provided, then what the final structure we will obtain after this process, what is known as cos light. The structure of the co-spherulite is relatively thick layer of both ferrite and cementite will be there. Such a slow cooling is called annealing. So the how we will identify this co-spherulite structure is, it is identified relatively with a thick layer of both ferrite and cementite. So both ferrite and cementite will have a thick layer. If it is appearing like that in the microscope, then we can ensure that the structure obtained is co-spherulite. So usually during a very slow cooling rate, then the structure obtained is what is known as co-spherulite, and the process of that slow cooling is simply known as annealing, that we will discuss in detail in the heat treatment process. Here sufficient time is available for the carbon in the austenite to diffuse and redistribute. That's why we will be obtaining that co-spherulite structure. Okay. So if you want to provide the slow cooling rate, means the heat content within the steel should not be allowed to escape quickly. So either we will be providing an insulating atmosphere, or we will be keeping the specimen within a furnace or something like that. So that anyway we will not allow the heat content of the specimen to escape quickly. So then only we can go for the slow cooling. That slow cooling process. And finally, if we are getting co-spherulite, then that heat treatment process is simply known as annealing. Okay, a somewhat faster cooling rate by air cooling. See, if you want to increase the speed of the cooling, let's see the curve 2. This is somewhat a quicker cooling compared to the curve 1. This fast cooling is provided, or we can say it as a medium cooling. That medium cooling is actually provided by cooling the specimen in the presence of the air. Just the specimen is allowed to cool in the air. That is what is happening in that cooling process. A somewhat faster cooling rate by air cooling lowers the effective range of transformation of the temperature. With the decrease in the temperature, carbon diffusion rate decreases. So you have seen that here, since the slow cooling is provided, carbon will get enough time for the diffusion and for the redistribution. But here, since the cooling process is not slower or faster cooling is there, so with decrease in temperature, carbon diffusion rate decreases and layer becomes progressively thinner. Instead of getting thick layer, we will be having thinner layers of cementite and ferrite. So that structure, that thin layered structure produced is termed as fine perlite. So instead of coarse perlite, we will be getting the structure of fine perlite. Here the steel is said to be normalized to yield fine perlite. So that heat treatment process of cooling the specimen in the presence of the air, just or simply the losing the heat to the atmosphere, that process is simply known as normalization. Okay, or simply normalizing. This is the graph I have already shown here. That we will come to this graph once again after explaining everything. The transformation of the austenite to perlite is suppressed by rapid cooling. So see, if we are still increasing the fastness of cooling, or more fast we are cooling, assume that, then what happens is the transformation of the perlite, transformation austenite to completely to perlite is, we are actually suppressing. We are not allowing the austenite to completely transform into the perlite, or the time for that complete transformation we are not providing. We are quickly cooling it down. So in that case, what happens is, if the austenite is held in isothermally below nose temperature, it transforms to bainite. Then the structure we will obtain is known as bainite. That means if completely all the austenite is transformed into cementite and ferrite, then we will call it as perlite. If complete transformation is not there, or time for complete transformation we are not providing with a faster cooling rate, then what happens is, of course, untransformed austenites will be there. That structure is, that combination structure of perlite plus austenite is simply known as bainite. Here cementite particles are short needle embedded in plates of ferrite. So how we will identify this structure is, the cementite particles are short needled embedded in plates of ferrite. That is how we will identify the presence of bainite structure. Okay. So bainite itself is divided into in two forms based on the cooling rate. If cooled slower than the bainite obtained is called upper bainite. So just below the normalizing temperature, if you are cooling in a particular temperature just below the normalizing temperature or air cooling temperature, then the structure finally will be obtained is known as upper bainite, or simply it is known as sorbate. If further we are decreasing the temperature or further we are increasing the cooling rate, then the final structure obtained is simply known as bainite, or otherwise it is known as trusite. Okay. uh, if another possibility is, if we are still increasing the cooling rate or the temperature difference we are increasing, then what happens is there is no transformation into the pearlite structure. Directly the austenite is transformed into a newer structure, that is what is known as martensite. If the metastable austenite is cooled rapidly below bainitic range, austenite will not get enough time to transform to ferrite cementite mixture. Instead it transforms to martensite. Directly it is transformed into a new structure, that is what is known as martensite. This cooling rate is achieved by quenching in water. That quick cooling is achieved by quenching in water. This process you might have seen in that smithy work and all. The tools and all, they have heated, after heating they have dipped it in a particular water kept nearby. So ക്വിക്ക് കൂളിംഗ് ഈസ് അച്ചീവ്ഡ്. നമ്മളിങ്ങനെ കൊല്ലപ്പണിക്കാർ ഇത് ആലയിൽ വെച്ചിട്ട് ചൂടാക്കി ഒന്ന് ഉരുക്കി വന്ന് അതിൻ്റെ മുകളിൽ പണിയൊക്കെ എടുത്തതിന് ശേഷം അതൊരു കൊടിൽ പോലെ തന്നെ കൊണ്ട് പിടിച്ചിട്ട് തൊട്ട് സൈഡിൽ വെള്ളം വെച്ചിട്ടുണ്ട്, അതിലേക്ക് മുക്കി പിടിക്കുന്നതാണ്. അത് നല്ലൊരു നല്ലൊരു സൗണ്ടൊക്കെ ആയിട്ട് അതിലങ്ങ്, അപ്പോൾ അതിനെയാണ് എന്ത് പറയുന്നത്, ക്വിക്ക് കൂളിംഗ് ക്വെഞ്ചിങ് എന്ന് പറയാം. അപ്പോൾ അതിൻ്റെ തൊട്ട് മുകളിലുള്ള, ഇഫ് യു വാണ്ട് ടു പ്രൊഡ്യൂസ് ബെയ്നൈറ്റ് or further improved property, then sometimes instead of water we will be using oil cooled bath. അപ്പോൾ സാധാരണ ഈ എൻജിൻ ഓയിലൊക്കെ ഉണ്ടാവും, അതിൽ ചിലപ്പോൾ മുക്കിയിട്ടും ചെയ്യാറുണ്ട്. ബോത്ത് ആർ ഫൈനലി വിൽ ബി ഒബ്റ്റെയിനിങ് martensite. Okay, here you can see that transformation. Austenite gamma structure will call it as FCC structure, 0.8% carbon. On cooling, transform into ferrite alpha. Simply ferrite is known as alpha, represented by alpha, and it is in BCC, 0.02% carbon, plus cementite Fe3C. That is the chemical formula for cementite, Fe3C. Orthorhombic in structure, 6.67% carbon. So these two combined, ferrite plus cementite, is simply known as pearlite. Now this is the same graph we have drawn here. This graph is here. This graph shows how it is drawn, that A1, A2, everything, how you got that is represented there. Here this is a particular TTT diagram for a eutectoid steel, and you can see that above this region you see the for a slow cooling rate, that is curve 1, above that one we will be obtaining coarse pearlite, and just below this curve we will be getting fine pearlite. Both are possible. Coarse pearlite initially we will get, if much faster cooling, then fine pearlite. After that we will be getting bainite. See, within this region we will have the bainite. In the upper portion we will have upper bainite, and the lower portion we will have the bainite itself, and below this one we will have the martensite plus austenite. Okay, so for a much faster cooling, directly from austenite we will be getting martensite and austenite. See, in this region we will have completely austenite. See, to the left of this curve we will have complete austenite. In this region transformation will take place, so austenite plus pearlite will be there. In this region what will be there is based on the cooling rate. If slow cooling is provided, then we will be getting either coarse pearlite or fine pearlite. That too depends on the cooling rate between these two. If much slower cooling rate is there, then of course we will be getting coarse pearlite. If slightly higher cooling rate is provided, then we will be getting fine pearlite. So above this line we will have pearlite plus austenite. In this region we will have pearlite plus austenite structure. So below this region we will have bainite plus austenite structure. Sorry, in this region, within this region we will have pearlite plus austenite structure. Here the entire this region we will have, to the right of this curve, from this point to this one. So right of this curve we will have pearlite structure. This will be in the upper region we will have coarse pearlite, lower region fine pearlite. So below this region, to the right of this curve we will have bainite. So in the upper portion we will have upper bainite, in the lower portion simply bainite. So in this region, below this horizontal line, in this region it is a combination of transformation is from austenite to bainite only, so not to pearlite. So here we will have bainite plus austenite in this region, and below this region we will have direct martensite. So martensite plus austenite will be there in this region. So that is all about TTT diagram. Okay, so ആക്ച്വലി എന്താ സംഭവിക്കുന്നത് വെച്ച് കഴിഞ്ഞാൽ നമ്മൾ ഡിഫറൻറ്റ് കൂളിംഗ് റേറ്റിനനുസരിച്ചിട്ടാണ് നമുക്ക് ഫൈനലി എന്താണ് കിട്ടുക എന്നുള്ളത് തീരുമാനിക്കുക. ഇപ്പോൾ നമ്മൾ 727 ° സ്പെസിമെൻ ഉള്ളത്, അതിനെ നമ്മൾ എന്ത് ചെയ്യുകയാണ്, കൂൾ ചെയ്യുകയാണ്. കൂൾ ചെയ്യുമ്പോൾ നമ്മൾ കൂൾ ചെയ്യുന്ന ബാത്ത് ഒരു പർട്ടിക്കുലർ ബാത്തിൽ വെച്ചിട്ടാണ് കൂൾ ചെയ്യുക, കോൺസ്റ്റൻറ്റ് ടെമ്പറേച്ചർ വെച്ചിട്ടാണ് കൂൾ ചെയ്യുന്നത് ഈ TTT ഡയഗ്രാം വരക്കാൻ വേണ്ടിയിട്ട്. അപ്പോൾ ആ കൂളിംഗ് റേറ്റ് ആണ് ഫൈനൽ സ്ട്രക്ചറിനെ ഡിസൈഡ് ചെയ്യുന്നത്. ഞാൻ പറഞ്ഞു ഇപ്പോൾ 727 അതിനെ നമ്മൾ ഒരു 650 700 അടുത്ത് റേഞ്ചിലുള്ള ടെമ്പറേച്ചർ വെച്ചിട്ടാണ് കൂൾ ചെയ്യുന്നതെന്ന് വിചാരിക്കുക. അപ്പോൾ അങ്ങനെയാണെങ്കിൽ നമുക്ക് ഒരുപാട് ടൈം എടുക്കും ഇത് കൂളിംഗ് നടക്കാൻ വേണ്ടിയിട്ട്. കാരണം ഓൾറെഡി നമ്മൾ ഈ സ്പെസിമെൻ വെക്കുന്ന ബാത്തിൻ്റെ ടെമ്പറേച്ചർ 700 ഉണ്ട്, മറ്റേതിൻ്റെ സ്പെസിമെൻ്റെ 700, ഓൾമോസ്റ്റ് അതിനേക്കും കുറച്ചുകൂടെ ഹയർ ടെമ്പറേച്ചർ. അപ്പോൾ രണ്ടും ഈക്വൽ ആയിട്ടുള്ള ടെമ്പറേച്ചറിലാകുമ്പോൾ ഹീറ്റ് ട്രാൻസ്ഫർ നടക്കാത്തതുകൊണ്ട് കൂളായി എടുക്കണം, കൂളാവണം കുറേ ടൈം എടുക്കും. നമ്മൾ നല്ല തിളക്കുന്ന വെള്ളം എടുത്തിട്ട് അത്ര തന്നെ അതിനടുത്ത് തന്നെ ചൂടിൽ വേറെ വെള്ളത്തിൽ ഒഴിച്ച് കഴിഞ്ഞാൽ ചൂട് പെട്ടെന്ന് കുറയോ ഇല്ല, അതാണ് സംഭവിക്കുന്നത്. അതാണ് സ്ലോ കൂളിംഗ് എന്ന് പറയാൻ കാരണം. നേരെ മറിച്ച് നല്ല തിളച്ച വെള്ളത്തിൽ പച്ചവെള്ളത്തിൽ ഒഴിച്ചാൽ എന്താ പെട്ടെന്ന് വെള്ളം ആ ചൂടുവെള്ളത്തിൻ്റെ ടെമ്പറേച്ചർ കുറയും. അപ്പോൾ അതിനാണ് ഫാസ്റ്റ് കൂളിംഗ് എന്ന് പറയുന്നത്. അതേ പ്രോസസ്സാണ് നമ്മളിവിടെ യൂസ് ചെയ്യുന്നത്. നമ്മൾ ആദ്യം നമ്മളുള്ളതെന്ന് വെച്ചാൽ ഈ ചൂടാക്കിയ 727 ° ചൂടാക്കിയ സ്പെസിമെനാണ് നമ്മൾ എന്ത് ചെയ്യുകയാണ്, നമ്മളൊരു 650 ഡിഗ്രിയുള്ള സോൾട്ട് ബാത്തിലേക്കാണ് വെക്കുന്നത്. അപ്പോൾ ഡിഫറൻസ് ആകെ എത്രയേ ഉള്ളൂ, 50 + 27, അപ്പോൾ ഒരു 77 ° ഡിഫറൻസേ ഉള്ളൂ. അപ്പോൾ സ്ലോ കൂളിംഗ് ആണ് നടക്കുക. അപ്പോൾ അങ്ങനെ സ്ലോ കൂളിംഗ് നടന്നു കഴിഞ്ഞാൽ നമുക്ക് കിട്ടുന്ന ഫൈനൽ സ്ട്രക്ചറിനെയാണ് കോസ് പിയർലൈറ്റ് എന്ന് പറയുക. പിന്നെയും കുറച്ചും കൂടെ താത്തി എന്ന് വിചാരിക്കുക, അത് 600 എത്തിച്ചു എന്ന് വിചാരിക്കുക. അപ്പോൾ കുറച്ചുകൂടെ ടെമ്പറേച്ചർ ഡിഫറൻസ് ഉണ്ട്. അപ്പോൾ കുറച്ചുകൂടെ പെട്ടെന്ന് നമുക്ക് ഈ സ്പെസിമെൻ തണുത്ത് കിട്ടും, കൂളിംഗ് റേറ്റ് കൂടി. അപ്പോൾ അങ്ങനെ വരുമ്പോൾ കിട്ടുന്ന സ്ട്രക്ചറാണ് ഫൈൻ പിയർലൈറ്റ് എന്ന് പറയുക. അതിലും കൂടുതലുള്ള കൂളിംഗ് റേറ്റ്, അതായത് ടെമ്പറേച്ചർ ഡിഫറൻസ് പിന്നെയും നമ്മൾ കൂട്ടിയെന്ന് വിചാരിക്കുക. അപ്പോൾ അതായത് ബാത്തിൻ്റെ ടെമ്പറേച്ചറാണ് നമ്മൾ കുറക്കുന്നത്. ടെമ്പറേച്ചർ ഡിഫറൻസ് കൂട്ടാൻ മീൻസ് നമ്മുടെ സ്പെസിമെൻ ടെമ്പറേച്ചർ 727 മുകളിലുള്ള ടെമ്പറേച്ചർ ഫിക്സഡ് ആണ്, ഓസ്റ്റനൈറ്റാണ് ആ സ്റ്റേജിൽ ഉണ്ടാവുക. പക്ഷെ നമുക്ക് കുറക്കാൻ പറ്റുന്നത് എന്താ, ഈ തണുപ്പിക്കുന്ന ബാത്തിൻ്റെ ടെമ്പറേച്ചറാണ് നമുക്ക് കുറക്കാൻ പറ്റുന്നത്. അപ്പോൾ അത് നമ്മൾ പിന്നെയും കുറച്ച് കൊടുത്തു കഴിഞ്ഞാൽ ഡിഫറൻസ് കൂടുമ്പോൾ എന്താ ഫാസ്റ്റർ കൂളിംഗ് നടക്കും. അങ്ങനെയുള്ളതാണ് ഒരു കേവ് 3 പറഞ്ഞിരിക്കുന്നത്. അപ്പോൾ ഒരു സ്റ്റേജ് കഴിഞ്ഞാൽ പിന്നെ നമുക്ക് എന്ത് കിട്ടില്ല, പിയർലൈറ്റിലേക്കുള്ള ട്രാൻസ്ഫോർമേഷൻ ഉണ്ടാവില്ല. അതായത് കംപ്ലീറ്റ് ആയിട്ട് പിയർലൈറ്റ് മാറാനുള്ള ടൈം നമുക്ക് കിട്ടില്ല. അപ്പോൾ കുറേ ഭാഗം നില ഓസ്റ്റനൈറ്റ് ആയിട്ട് ഉണ്ടാവും, കുറച്ച് എന്തായിട്ടുണ്ടാവും സിമെൻറ്റൈറ്റ് പ്ലസ് ഫെറൈറ്റ് ആയിട്ട് മാറിയിട്ടുണ്ടാവും. അപ്പോൾ അങ്ങനെയുള്ളൊരു കോമ്പിനേഷനാണ് എന്ത് പറയുന്നത്, ബെയ്നൈറ്റ് എന്ന് പറയുന്നത്. ബെയ്നൈറ്റിനെ തന്നെ കുറച്ചുകൂടെ സ്ലോ കൂളിംഗ് ആണ് ഉള്ളതെങ്കിൽ അപ്പർ ബെയ്നൈറ്റ് ആണ് ഉണ്ടാവുക. കുറച്ചുകൂടെ അധികം കൂളിംഗ് റേറ്റ് കൊടുത്തു കഴിഞ്ഞാൽ എന്ത് സംഭവിക്കും, ബെയ്നൈറ്റ് മാത്രം ഉണ്ടാവും. അതിലും കൂടുതൽ ഫാസ്റ്റർ കൂളിംഗ് ആണ് നടക്കുന്നതെങ്കിൽ എന്താ സംഭവിക്കുക, നല്ല ടെമ്പറേച്ചർ ഡിഫറൻസ് ഉണ്ട്. നമ്മളൊരു 200 ഡിഗ്രി 250 ഡിഗ്രിയിലാണ് ബാത്ത് ടെമ്പറേച്ചർ വെച്ചതെങ്കിൽ ഡിഫറൻസ് 500 മുകളിൽ വന്നു. അപ്പോൾ ഫാസ്റ്റ് കൂളിംഗ് നടക്കും. അപ്പോൾ പെട്ടെന്ന് സ്പെസിമെൻ തണുക്കും. അതാണ് ഈ വെള്ളത്തിലൊക്കെ വെച്ച് തണുപ്പിക്കുന്നത് പറയുന്നത്, മനസ്സിലായില്ലേ. അപ്പോൾ അങ്ങനെയുള്ള പ്രോസസ്സാണെങ്കിൽ അതിനെന്ത് പറയും, ഫാസ്റ്റ് കൂളിംഗ് ആണ്. അങ്ങനെയാണെങ്കിൽ നമുക്ക് കിട്ടാവുന്ന സ്ട്രക്ചർ എന്ന് വെച്ചാൽ ഈ ഓസ്റ്റൻ ഫെറൈറ്റും സിമെൻറ്റൈറ്റും ഒന്നും ഉണ്ടാവില്ല, പകരം ഡയറക്റ്റ് എന്താണ് മാർട്ടൻസൈറ്റ് എന്ന് പറയുന്ന സ്ട്രക്ചറാണ് ഉണ്ടാവുക. ഇതാണ് ഇതിൻ്റെ ബേസിക് എന്ന് പറയുന്നത്. അതിൽ തന്നെ നമ്മൾ ആദ്യം പഠിച്ചു, നമ്മൾ സ്ലോ കൂളിംഗ് കൊടുക്കണമെങ്കിൽ ഒരു ഫർണസിലോ അങ്ങനെ എന്തെങ്കിലും ഒരു എന്താ പറയുക ഇൻസുലേറ്റഡ് എൻവയോൺമെൻറ്റിൽ വെച്ചിട്ട് വേണം തണുപ്പിക്കാൻ വേണ്ടിയിട്ട്. എയറിൻ്റെ കോൺടാക്റ്റ് ഉണ്ടാവില്ല. അതിന് പറയുന്ന പേരാണ് അനീലിംഗ് എന്ന് പറയും. പിന്നെ അത് കഴിഞ്ഞിട്ട് എയറിൽ വെച്ചിട്ടാണെങ്കിൽ നമ്മളതിനെ പറയുന്നതാണ് നോർമലൈസേഷൻ എന്ന് പറയും. ഓക്കെ, അതുപോലെ ഇപ്പം ഫാസ്റ്റർ കൂളിംഗ് റേറ്റ് വെള്ളത്തിൽ മുക്കിയിട്ടൊക്കെ തണുപ്പിക്കുന്നതിനാണ് എന്ത് പറയുന്നത്, കൊഞ്ചിങ് എന്ന് പറയുക. അപ്പോൾ അത് രണ്ടുണ്ട്, ഓയിൽ കൊഞ്ചിങ് ഉണ്ട്, ഓയിൽ ബാത്തിൽ വെച്ചിട്ട് ചെയ്യുന്നുണ്ട്, അതുപോലെ വാട്ടറിൽ വെച്ചിട്ടാണെങ്കിൽ അപ്പോൾ ഡിഫറൻ്റ് ആണ്. ഓയിലിൻ്റെ ആകുമ്പോൾ വെച്ചാൽ കുറച്ചുകൂടെ അത് വിസ്കോസിറ്റി കുറവുണ്ട്, ഹീറ്റ് ട്രാൻസ്ഫർ കുറച്ചുകൂടെ ടൈം എടുക്കും, പെട്ടെന്ന് തണുക്കില്ല. നേരെ വെള്ളത്തിലാണെങ്കിൽ പെട്ടെന്ന് കൂളിംഗ് നടക്കും. അപ്പോൾ ഫാസ്റ്റർ കൂളിംഗ് റേറ്റ് ആണ്. ഇത്രയാണ് ഇതിൻ്റെ നട്ട്ഷെൽ എന്ന് പറയുന്നത്. അപ്പോൾ നന്നായിട്ട് പഠിക്കുക. ഈ ഗ്രാഫ് വളരെ ഇമ്പോർട്ടൻ്റ് ആണ്, ഡയറക്റ്റ് ചോദിക്കാനുള്ള സാധ്യതയുണ്ട്. ഇനി ഇതിൻ്റെ കൂടെ തന്നെ CCT ഡയഗ്രം കൂടി ഉണ്ട്, നമുക്ക് ഡീറ്റെയിൽഡായിട്ട് പഠിക്കാം. ഓക്കെ, താങ്ക് യു.